When we were faced with the urgency of climate change, we wanted to put the tools that we had as experts in coating systems and surface area to help develop a solution. So we went to our team and we decided to work on a climate change solution that mimicked the way that lichen work in nature. Lichen is comprised of two organisms, a fungus and an algae.
Those microscopic algae are spread on almost every surface you can imagine. If there's any way they can grow, they will grow. And it's a little teeny tiny photosynthetic engine.
So Team Lichen is doing a lot of what nature is doing. Algae are already capturing the CO2. One difference is that in nature, that carbon fixation is a cycle, right? So they capture the carbon, then eventually it's released back to the atmosphere. So in this case, they're actually fixing the CO2 and they're going to leave it there. Sequester the CO2, that's right.
Our first field unit is in Tracy, California. That's where we will be capturing and sequestering 1,000 tons of CO2.
We had to think about how are we going to do this in the real world. Well, you could build huge buildings, you could build huge greenhouses, you could do all that. But there were already existing things, intermediate bulk cargo containers.
What we've really done is give nature that helping hand, where now we take those algal cells and put them in this system that just gives them a lot more area to grow in.
Put this into a modular system and take advantage again of our expertise in coatings as well as polymeric systems to actually go vertical.
We can now put these materials vertically stacked and still have that good light penetration and air exchange.
Then you have a better chance of pulling down a whole lot of carbon dioxide.
What we see Thomas doing here is inoculating our porous cellulose matrix, the material that we use to let the algae grow. And then he'll place that into a container, allow it to be open and have access to the air, and continue to grow. So now moving to these bigger sheets, we see much greater growth of the algae, much greater CO2 capture.
There's all sorts of air pockets within this thing so that the algae get plenty of water, plenty of nutrients, and plenty of sunshine. And we will then infuse these spaces like this with all kinds of functionality that actually helps the algae grow.
And we have a history of coatings technology that deals with other issues like contamination, unwanted growth, keep our algae viable and healthy in that system.
We have to seal these containers completely so that no additional CO2 can get in. Then we add the CO2 sensor. When we monitor it, the slope of that CO2 concentration drop is almost straight down. We can simply wring out the liquid from each sheet of material and collect liquid that contains most of the algae that grew over whatever the growth period was.
We're going to pour the harvest that we collected on the previous days. It's going to funnel into the filter that's below and filter out the algae on the inside of the bag, and then this tote so we can cycle it back into our PCMs again.
In the lab, our next step would be to collect this biomass and dry it to almost completely dry using a solar oven. We typically then transfer that into a small pan and fully dry to see exactly how much biomass yield we got out of our experiment. That's a big accomplishment on its own that we've grown that biomass, but really in order to truly sequester that, you run it through pyrolysis, and then the char amount that you receive at the end is considered permanently sequestered.
There are an estimated 50 to 100,000 different species of algae. They are enormously diverse in their genetics and their biochemistry, and in the conditions that they grow under. That gives us an enormous potential to expand where we can put these facilities for capturing CO2 using algae.
I feel so fortunate that we had this team of experts that we could put to work on this problem. 1,000 tons is just the beginning.